It's a real pleasure to have Professor Beatrice Bonga with us today. Beatrice, so I'll just have a little introduction to Beatrice. She did her PhD with Professor Abhay at Penn State University. Her thesis was on how gravitational radiation can be defined when one has a positive cosmological constant. The normal definition assumes that far away from any source, you have space-time is completely flat. But of course, our universe has a small but positive cosmological constant, non-zero cosmological constant, and that changes a lot of the asymptotic structure. So she did some very important work on this mathematical work with Abhay and Aruna Keshavan. And I think that sort of started off a series of very interesting papers in this broad direction. Beatrice then went on to doing a postdoc at the Perimeter Institute, which is where I first met her, I think, or perhaps at a conference before that. And after that, she joined the faculty at Radboud University, which is in the Netherlands. She's worked on myriad aspects of GR and also a little bit on quantum gravity phenomenology. And when I say myriad aspects, there are things that range from astrophysics to all the way to mathematical GR. So she really, in terms of the breadth of her experience in GR, even though she's a young faculty, I think it's quite impressive. Today, she's going to tell us about some new work on resonances in black hole and neutron star systems and how they give rise to gravitational radiation signatures that might be captured in the next generation of gravity wave detectors. So welcome, Beatrice, to RRI. I wish you could have visited, and I hope you will do so in the future. Just to tell everyone, Beatrice is very happy to take questions during the talk because she'd rather we engage with her than not. And we will, in true RRI tradition, hopefully do that. So on to you, Beatrice. Thanks for agreeing to give this seminar.
Wow, that is such a nice introduction. I don't think anyone ever introduced me like that. Thank you very much, Timothy. It's indeed a pleasure to be here. Of course, I would have even liked it better to come to India. Such a beautiful country. I've only made it up to the north, but well, who knows for the future. So today's talk indeed is going to be a bit in the setting of more the astrophysics side of the work I've done, and it is on resonances in general relativity. So just as a reminder of resonances, what are they, or this a very intuitive way of thinking about them. I think this is a beautiful classic example that probably many of you know, right? A resonance happens when you have sort of a matching of frequencies. So if I have some external force, say, I am going to sing, and, in my case, I cannot, but, if you can keep your pitch very well, and if you can match your pitch to the natural frequencies of an object, right, such that the frequencies match, then you can get a very efficient transfer of energy. So the energy in the sound waves can be transferred to mechanical vibrations. And this can lead to big effects, like, for instance, in this case, the shattering of the glass. Now, resonances happen in all kinds of settings, right? Also in stellar systems, right? So, for instance, if I now have some type of tidal interaction and a binary system, or if you want, even, a triple system or something like that, and you have a matching of frequencies, you can also get an efficient transfer of energy to, say, the orbital energy, and that is something that can then again affect something like the gravitational wave. So this is the basic principle of today's talk. And we're going to talk about resonances in two different settings. So first, I'm going to talk about the setting with 3 different black holes. And then in the second, shorter part of the talk, I'll talk about resonances in binary neutron stars. So let's get started. So here what you see is an EMERY, which is shorthand for an extreme mass ratio inspiral. So this is a system where we have a central massive black hole of, say 10 to the 5, 10 to the 7 solar masses that is orbited by a smaller one, say 10 to 100 solar masses. And these systems, they're very cool and they're very exciting sources of gravitational waves for the LISA observatory, which is well, I said not so nicely, but essentially it's LIGO in space. And it's going to be launched in 2034 or so. And the reason why we don't see these systems with LIGO is that their frequency range is not in the Hertz regime, but it's in the millihertz regime. Now, one of the most exciting things of these systems to me is that we will see these systems for a very long time, right? So, for years. Right, all these LIGO signals, they're incredibly short, right? They're less than a second typically, if you talk about the merger of two binary black holes. But these systems you'll see for a very, very long time. So essentially what it means is that we get to really understand very well or probe very well the space-time structure of this central massive black hole through observing these gravitational waves. Now, typically, right, when people look at these systems, they have said, well, let's model them as completely isolated, right? So let's say, we have a massive black hole, small one in vacuum. And we ask ourselves the question, well, what about, if I have another black hole nearby, another small black hole nearby? How would that change the picture? Then, of course, you first have to ask yourself the question, okay, what's a realistic distance? I mean, as a theorist, I can put this black hole, of course, anywhere I like, but what would, happen physically in nature? Now, of course, we don't really know, right? Because we have not observed these systems yet. So we don't also know what a realistic distance is. But of course, we have, models and ideas out there. So for instance, if you look at some type of Fokker-Planck simulation, people have found that, well, you could expect a population of about 40 solar mass black holes close to Sagittarius A star with some medium distance of about 5 AU, right? Where AU is the distance from Earth to Sun, the standard astrophysical distance. Other people have simulations and claims and ideas that brown dwarfs can be the approximate distance of 30 AU for Sagittarius A star. And if you were to do some type of back of the envelope calculation where you say, okay, well, we have some expectation for how many EMERYs we will see. So, and if you take that expectation value sort of for where you would see, that means also that you can estimate where the next black hole has to be consistent with that rate, right? And that would give you something of a distance of about 4 AU.
Can I interrupt already?
Yes, of course.
Where does one, so I don't know what this Fokker-Planck simulation is, but also what are the kinds of things that actually go into these simulations? Because what's the kind of physics that you assume and so on that goes into it?
Oh, well, that depends actually very much on which astrophysicist you ask that makes such a simulation. But typically what goes into these things is, well, you need some type of formation mechanism for black holes. So you could say, okay, well, these lighter black holes, they're all formed through, say the collapse of stars. So then first you want, an idea of how many stars you have of a certain type, etc., and how many of them will then form a black hole. And then you also want, in this particular case, how many of them will be captured by such a central massive black hole. And in that setting, you typically need things also like, the gravitational interaction, right, between these different bodies and things like that. So lots of different physics go into these models. They're not so easy actually to reproduce
These are kind of like very souped up n-body simulations, I suppose. And with
yeah, absolutely. Yeah, that's correct. And the interesting thing is all these estimates, they're all done for something that we will call like the dry channel. And the dry channel is essentially the traditional formation scenario for an EMERY, where you have a central black hole and stars around it, but no disk or something like that. Recently, a new formation channel has been proposed, where actually in active galactic nuclei, where you often also have a central massive black hole and then a disk around it. And people initially thought that these disks, they're somehow the migration of these black holes is too slow. They don't get so close to the central black hole. They get trapped, and you don't get EMERYs. But people found actually that there were some assumptions in those models that are incorrect. So now we even expect more EMERYs than we did initially, because we have this whole new way of creating more EMERYs. And in this second channel, you expect even more close items, because the disk is quite busy, if you want. So let's, for the purposes of this talk and for concreteness, we have a bunch of numbers, between 4 and 30 AU. Let's put this extra guy out here at, say, 5 AU as a canonical distance. You can say, okay, 5 AU, that is pretty far away, right? That is 5 times the distance Earth-Sun. At this point, you really don't need to worry about general relativistic effects. You can say, okay, let's first estimate the effect of this guy on this system, just using some Newtonian physics. And if you do that, right, we say, okay, well, let's look at this at this parameter, right, which is the mass of the star over the distance cubed, right, which is essentially a measure of the tidal force. And if you plug in those numbers for, say, putting this 5 AU and this M star, say 30 solar masses, and this mass, the mass of Sagittarius A star, you find a ridiculously small number, right? You find something that's 10 to the power minus 12. So typically you would say, okay, well, let's not worry about this extra third object. Let's not worry about this tidal perturber. It really is so small, we don't need to worry about it. And this is generically true, except, of course, that's the title of the talk, except, of course, when you hit a resonance. Now, what kind of resonance am I talking about here? Well, resonances, right, as you remember, right, we have to have a matching of frequencies. So first of all, we have to ask ourselves the question, which frequencies are you even talking about? So if you look at this plot, actually, this plot of this small guy, without the tidal perturber going around the central massive black hole, you already notice, wow, that is actually a pretty complicated orbit. Right? Typically, if you just look at the two-body system in Newtonian physics, right, you can go to the center of mass frame and you just get an ellipse. Right? So you just need one frequency to describe the system. But here, because of strong gravity effects, right, you get much more complicated orbit. And in fact, as it turns out, you need 3 different frequencies to describe this orbit. And that is shown in this figure. So, if you're far away from the central massive black hole, in other words, when your semi-lattice rectum is large, right, that means that these 3 frequencies are indeed essentially roughly the same, right? They reduce to, our Newtonian physics case. But as you get closer to the central massive black hole, these 3 frequencies really become different, as you can see here. And a resonance happens when essentially these 3 frequencies become commensurate, as we will see. So typically, for instance, don't worry about the details of this figure, but one way to describe things, how things are happening in this system, is to look at, say, the angular momentum. And the angular momentum, as this small guy is going around the central one, it oscillates a bit because, there's gravitational radiation emitted and things like that. And, over time, it will slowly decay, but you really need a very long time. But when you hit a resonance, boom, something like this can happen, right? You get a big change. And that's exactly, at this time when the orbital frequencies, if you add them all with integer numbers, so mk and n are integers, when that's 0, you can get something big like this. Now, the rest of part 1 of this talk about the black hole section is, why is this the resonance condition? We'll see that naturally pop up. How do you actually calculate the size of the jump, right? And what is the effect on the waveform? So is this something that we can see with gravitational wave detectors or not? So to get started, one very useful way.
Can I again ask a question? So when
yes,
you talk
please.
ordinary resonances, you say, there's something that there's a transfer of energy. So
yeah.
In this case, okay, so there's a natural set of 3 frequencies. Are we transferring from one mode to the other 2, or what is the transference of energy that's happening here in this?
So
this one is just a 2-body system. You don't have your third guy yet, right?
Good. So yes, good. So the interesting part is, okay, so the third guy. So here, actually, you can get resonances in this system too.
Okay.
Without the third guy, which we will see actually in a bit. And then I'm going to add the third guy in as well.
Okay.
It is a good question. So in this system, when you just have 2 and you have a transfer, when you have a resonance, it is something that we call a self-force resonance, and it's a transfer between, well, if you want, gravitational radiation and orbital energy.
So does it then radiate away, or is that what happens?
Yeah, so it can go either way. So it can get, it can gain orbital energy, so take away, or or it can lose orbital energy. It can really go both ways. Yeah, just, yeah, kind of nice. So indeed, let me take out the third perturber and just focus on this simpler system. And the reason I'm going to do that also is indeed because similar resonances happen, and the mathematical framework we're going to build up slowly to understand how this works. So you'll see actually, once we understand this system very well, it's very easy to throw in that third body. So as you know, many systems, it's convenient to go to action angle variables, right? So this system, there are many ways you can describe the orbit, right? You can just use coordinates and just plug and chuck, but certain set of coordinates are and variables are more useful than others. So in this system, right, if we say, if we think about the system, right, we know that the central object is very massive, and this guy is very light. So, to zeroth order, right, just, make an approximation and say, okay, this one is so light, it is as light, as a test particle. Right? So what it does, as we know from general relativity, test particles, they just move along geodesics. Right? So to zeroth order, this guy is just following a geodesic. And the nice thing about geodesics around rotating black holes, right, is that we can actually solve them analytically completely, because there are 4 constants of motion, right? The mass of the rest mass of the system, its orbital energy, its angular momentum in the z direction is something that we call the Carter constant. So as a result, since you have these 4 constants of motion, you can show that the geodesic equation is completely integrable, And therefore also that action angle variables are particularly useful, right? And in those variables, right, we have some constants of motion, the actions. And if you want, right, you can just think of those actions as just being some linear combination of these constants of motion. And then we have the angles, right? And the angles, because they evolve at a constant rate. In fact, actually, this defines what we mean by that omega r, omega theta, and omega phi. Right? This is a definition of the orbital frequencies of this type of motion. Of course, we know, right? Well, yeah, before I introduce a perturber, we know already, right, that the motion, in fact, is not geodesic, right? Because, well, this is not quite a test particle, it has some mass. And in fact, I hope you know, but intuitively, right, the physical reason why it's not following a geodesic is because it will emit gravitational waves, right? As it's going around the central massive object, it's losing energy and therefore it's getting closer. So, over time, it will spiral inwards into this central object. So of course, gravitational radiation changes that description. And if you want, that goes typically by the name of cell force. So what we now do, right, we introduce a small parameter, typically denoted by eta, which denotes the mass ratio. So it's the mass of the small object over the mass of the larger object. And, then there's some complicated correction formulas that will tell you, well, actually now in this case, the actions are no longer exactly conserved, they're changing slowly. And similarly, right, the angles now aren't just changed by the frequency, but there's some formula there. Now, these formulas actually, turn out, if you really go and start to derive them, they're really quite complicated. And you could maybe say, okay, well, that's complicated, put them on a computer, but even that, it's not so tractable. So what people do is to say, okay, well, these formulas are complicated. Let's make, an additional assumption. Let's make this adiabatic approximation. So what you do in that approximation is essentially say, okay, well, I don't care about all the details of those functions, right? I don't care about exactly all the nitty-gritty bits. What I really care about is sort of its average behavior as you go around, the central massive object once, so to say. So you do this, use adiabatic approximation. So in a way, you do this kind of orbit averaging. And when you do that orbit averaging, as it turns out, you don't need to worry at all about this term. That one sort of drops out. And this is you only care about the average behavior of this term.
Sorry, are you saying that can you just go back to the first slide?
Yeah.
So you're saying that with respect to the angle variables, it's sort of still to leading order, you don't get this eta correction.
Correct. Yes.
Is there any, do you have any physical, I mean, I know that this is a very complicated system, so I don't expect this answer, but is there some reason why the angle variables have a particular, that the leading order approximation is small? I mean, is there some physical kind of understanding of that?
So I think, yes, so there is a sort of an understanding. So if you are thinking of this, these formulas, what they depend on, you can sort of split them into two pieces, as people say. They say something like, one piece is conservative, so it doesn't really change much on short timescales, and one piece really has to do with this dissipation, with radiation reaction. And as you split them, right, what sort of happens is that the radiation reaction is the thing that you need to worry about at leading order in this adiabatic approximation, and the conservative pieces sort of are only, again, at that next order bit. As it turns out, this formula really is made up primarily of conservative bits, if you want, and this one contains both information of the radiation reaction and the conservative bits. I don't have a really good intuitive reason why that would happen. I think this has to do also, with the underlying symmetries of the Kerr space-time. But let me think of a more intuitive reason why that would happen. But as of now, I cannot tell you exactly. But that's the reason why you don't need to worry about this term, but you do worry about the averaging of this term. It's a nice question.
Thanks.
So now the question, of course, is like, how do you actually calculate such an averaging? Like, how do you do that? Well, and as it turns out, averaging, especially in these action angle variables, is quite easy, right? Because these are proper, these Q theta and QR are proper angles, right? So they go from 0 to 2 pi, and I can do a nice Fourier decomposition. So I can write this function as an infinite sum, of course, over these k and n's, where these coefficients, right, they only depend on the actions, and here I have, my exponential. So, if we don't do any averaging, of course, this doesn't bias anything. But when you average, right, essentially what you do is you say, okay, well, I think this thing oscillates over time. So most terms will drop out if I do my averaging, and the only terms that don't drop out are the ones where it doesn't oscillate, right? And the terms where it doesn't oscillate, well, that's of course only when k and n are both 0. So this is great, right? Because now you really only care about the 0, 0 coefficient. This is, of course, generically true, except, of course, when this term up here doesn't oscillate. And when doesn't it oscillate? Well, if its time derivative, right, is 0. And if you remember, right, the time derivative of q theta, that was the definition of what omega theta is. And the time derivative of QR is omega r. So whenever this combination is 0, you should also add, of course, the coefficient that corresponds, right, to the value of k and n for which this holds. And that's the reason why this is the typical resonance condition. Now, to get you a little bit of an intuitive image for how this would look, right? On the left, I'm plotting some generic orbit, right? A generic geodesic going around the central black hole, which is in the middle. I have not shown it. And as you can see, the evolution looks, I mean, almost chaotic, right? It's pretty wild. But if we now focus on the figure on the right and project that evolution in our theta plane, we see that it sort of nicely, over time, completely traces out this two-dimensional surface. Now, when the resonance happens, we can look again at the left plot, and you may notice that, well, maybe it looks less crowded or something. But if I now look at the right plot, it's quite striking, right? It doesn't matter how long we wait. We're not filling out this 2D plane at all. We're really restricted to this one-dimensional subspace, right? To this Lee-Jia-Zhu figure. And that's also the reason, right? If we were to orbit average over, whenever the orbit is in a resonant orbit, right, what we're doing is we're averaging over this full 2D plane. But of course we shouldn't, right? Because it's not going over this full 2D plane. It's only restricted to this one-dimensional subset. So you really should be doing mathematically something different, right? Now, these self-force resonances, you may ask yourself the question, okay, well, this seems like a rather mathematical condition that, these frequencies, they have to be commensurate, as they say. Maybe, that actually never really happens in nature, or maybe it could be very well be the case. However, as people, before us, they showed actually, Well, these things do happen generically for EMERYs, even, you know, the ones that we observe in the LISA band, right, with the space-based version of LIGO, so to say. And what people also showed is, well, the jump size, or, you know, the effect is typically small, but if they happen early in the inspiral, they can lead to significant dephasing of the waveform. So that's something that means that, you know, it means that you can actually see this. And the bigger jumps happen when you have lower order resonances. So when the integers n and k are small. This is in fact actually true pretty much for any resonance you ever calculate. This is not, you know, unique to GR or black holes. This is, you know, just true for resonances in general. Small integer values typically lead to bigger effects. And what they also found is that the effect here is typically larger when you have more eccentric orbits. And why is that? Well, if you don't really have, you know, if you have a circular orbit, say, then in fact this omega r is essentially 0. So you don't really get any beating of frequencies, right? You don't really have a resonance to begin with. So you need you need significant eccentricities so that this omega r is, you know, significantly different from 0, and you really get this beating of these two frequencies. Now, what people also said, well, you know, for detection purposes, you might, you know, if you say you're going to see 1,000 EMERYs, you might lose a few percent, right? You miss out if you don't properly model for these self-forced resonances on a few of those EMERYs. But of course, they're quite critical for parameter estimation, right? You really get the wrong parameters of the system if you don't account for these resonances. So that was all about the self-forced resonances, which will happen in the setting of the two-body system. You know, how about that tidal perturber that I started to talk about? Well, we can do it really the same thing, right? So we have, again, action angle variables, but now with a tidal perturber. So what we've introduced here is extra terms, right? So here we have our self-force terms, right? The radiation terms, they're up here. But now we also have these tidal terms, which can be complicated functions and all of that. But there's one thing you should immediately notice is that these functions now also depend on Q phi, and not just on Q theta and QR. Now you may have asked yourself the question, actually, why before, like why does the self-force not depend on Q phi? And that has to do, right? If I look at, say, the curved black hole, right, a rotating black hole, and a small one going around it, it doesn't matter at which phi angle I am, how much radiation I'm emitting, because the curved black hole is axisymmetric. So things don't really depend on the angle phi. But of course, if I now have an extra perturber, right, that breaks that axisymmetry. So of course, these functions should depend on phi, unless of course I were to put the perturber exactly on the spin axis of the black hole, but that would be a highly contrived situation, of course. So what we can now do is, okay, we notice this difference, interesting. Let's do the same as we did with the other analysis. So let's use this adiabatic analysis. Again, we only need to focus in this case, right, on the averaging of this term. And when we do that, right, we notice that, okay, we can do the same thing as before. We do a Fourier expansion, but now, of course, this Fourier expansion also depends on MQ phi and not just on Q theta, KQ theta and NQR, right? There's this extra thing here because the function also depends on Q phi. This is nice in a way, because that means that if I ask myself the question, okay, when does this function not oscillate, right? So if we do this orbit averaging kind of thing, when it doesn't oscillate, well, that means that whenever m omega phi plus k omega theta plus n omega r is 0. So as you can see, this is a much, richer resonance condition, right? I have this whole extra dimension to create extra resonances. So these type of resonances, in a way, they should happen more frequently. And the nice thing is, even if I have a completely circular orbit, right, I have no omega r, then I can still get resonances between this m omega phi term and the k omega theta term, right? So these resonances happen also for low eccentricity orbits. So these tidal resonances are much more generic than these self-force resonances. And in fact, many of them happen, right? So as I said, they're very generic. So let's look at this plot and see what I mean by that. So if I have, say a central black hole that's spinning quite rapidly, 0.9, we expect them to be somewhat fast spinning typically. And if I have some orbit that, starts far away with some semi-lattice rectum, or far, it's not so far, but at 9m, it means that it's already in the Lisa band so that we can observe it. Then because of gravitational wave emission, right, the small black hole will get closer. So its semi-lattice rectum will shrink. And similarly, we also know this is a central result from Matthews and Peters in the 60s that showed that gravitational wave emission, typically, if you have some orbit, it will circularize orbits. So it means that this eccentricity, as you get closer to the central black hole, it's going to decrease. And as it, is getting closer and circularizes, we see that it hits these surfaces of -302, -320, etc. These surfaces are exactly the surfaces where this condition is satisfied with these numbers referring to K and M. So here you see, for instance, that if you have some prograde orbit, so you're co-rotating with the central black hole, you hit at least 4 resonances before you start plunging. And it doesn't matter if you're a prograde orbit or a retrograde orbit, the same would hold, right? Just the resonance surfaces are at slightly different locations, etc. But it's very generic. You'll have many resonances in, right? I can start with a different eccentricity, and but still with 0.9, right, I would still need to cross these surfaces. So you'll have many, many resonances, also for slowly spinning black holes, right? You don't need to be going around a fast spinning black hole. Also for slow spin, again, you have these surfaces. So the upshot is resonances occur pretty much across the parameter space. Now, of course, then the next key question is, okay, resonances happen, but do they have an appreciable imprint, right? Even if they happen, but their effect is so marginal that then you wouldn't see anything, right? So the next question is, what is the size of the effect? And I think this is kind of an interesting way to calculate. So here, what you see here is, in a way, what we're saying is, well, to the presence of that tidal perturber, what it does, right, it essentially induces a force, right, or it accelerates the EMERY die. And its acceleration, in fact, you can calculate quite generically using this formula, where for the experts in GR, this would be the curve black hole. Here we have the unit tangent factor to the geodesic, and here are some covariant derivatives of the metric perturbation. So I'm really treating the system as Kerr black hole plus a metric perturbation, and that metric perturbation is, caused by the presence of that tidal perturber. Now, the hard part of this calculation is to actually calculate this, and luckily for us, that was already done in the literature. So people have found ways to calculate this metric perturbation of a tidally perturbed Kerr. using techniques, solving the Tucholsky equation and then applying metric reconstruction. Of course, this is not, a beautiful analytic, nice results. There are lots of, again, approximations that you make in here. So what we assumed here is that the tidal field is stationary, right? So we assume that the extra third guy far away is not moving during the time of the resonance. And that's maybe not so reasonable, right? Of course, it's not static, right? We know that also the third object is moving, but the relevant time scale over which it should not be moving is, of course, the time of the resonance. And we see that this approximation is reasonably satisfied. But of course, this is something we would like to improve. And we only take into account the leading order part. So we only take into account the quadrupolar tidal field. Now, this is sort of, up until this point, you can do things still analytically in Mathematica. But if you start calculating this thing, you end up with, a file that is several MB of just analytic expressions. So this is where your analytics ends, and you should, start calculating numbers, because it's, impossible to do anything with that. And that's what we did. So then to calculate the jump size, right, we now sort of know the force or the acceleration caused by a tidal perturber. We find actually that the jump it causes, right, whenever I hit a resonance, is determined by two key factors. First, how long the jump lasts. And second, of course, how strong the resonance is. And so you can imagine, right, if the tidal field is stronger, right, if we put it closer, then of course the strength is larger and you get a bigger effect. So the things that the resonance strength depend on are this ratio, right, the mass of the perturber over its distance cubed, its sky location, so where exactly is it? Is it in the equatorial plane or is it offset? Also on the mass and the spin of the central massive black hole, and on the parameters of where the resonance happens. So whether this EMERY guy is very close or farther out, right? So the semi-lattice rectum of the small guy, its eccentricity, and also its orbital inclination. Now the duration of the resonance actually is set completely by the radiation reaction time scale. So by how fast the EMERY is spiraling inwards. So whenever the small guy is very close to the central black hole, right, it emits more gravitational waves. So the duration is shorter. And if it's farther out, right, it emits gravitational waves slower, so the duration is a bit longer. Now, these things, right, they're somewhat complicated, or for the purposes of this talk, I'm going to ignore the sky location because things are not so sensitively dependent on that. And what we're going to do is we're going to calculate the jump size depending on, these parameters, right? So on the spin of the black hole and these four, and I'm ignoring the masses and this ratio because those turn out to be very nice. They kind of like pull out, they're a constant overall factor. So their dependence, you can pull out easily. And the reason, so then in principle, right, I should be left with four parameters, A, P, E, and I. But, right, the fact that we're talking about a resonance, right, that puts a constraint on the parameters, right? So if I know these three, and I know a resonance of a particular type is happening, say the 3, 0, -2, or the 3 -4, 2, then I know what the value of the semi-lattice rectum is. So let's have a look. If I look at, for instance, right, how the rate of change of the angular momentum is affected on a resonance, right, we get this jump. And the jump, right, depends, as you can see, on the eccentricity. So larger eccentricities will lead to somewhat larger jumps. And here, right, this is the red line is the change in angular momentum. And the blue line is the change in that Carter constant. And this is for a particular type of resonance, right? So when 3 times omega r minus 2 times omega phi is 0. Now, right, we have 3 orbital parameters, right, that are crucial to describe the orbit, right? The angular momentum, the Carter constant, and the energy. Now, the reason why I'm not showing you the energy, right, the rate of change in the energy, is because the energy is not being changed across the resonance. And that has to do with the fact, right, that we approximated the system to be, that the tidal force is stationary. So because of that, right, your energy should not change. And of course we checked, it doesn't change. But so you can imagine a line around 0, or numerically 0 at least, where you see that the energy doesn't receive any jump across this resonance. Now there's one subtle point right here. I'm pretending as if, you know, these jumps are exactly this number. But of course there's a subtle point, right? So when I look at this expansion, right, of the force, right, e to the power I blah blah blah, what we want, right, is that the time derivative is 0, but it means you can have a constant phase here. Right, so I could, in this case, right, I can have still a phase e to the power I 3 omega r minus 2 q phi, right, at the time of a resonance. So depending on that phase, in fact, whatever that phase is, it modulates the size of the jump. So here you see sort of the size, here you see this value, what we've plotted. But in fact, right, the value really is modulated by the phase. So you can have situations where you go through resonance and the phase is exactly, you know, say here, such that you don't feel any jump at all, right? Or the phase is such that, you know, you feel the maximum jump size, which can happen too, of course. So for the remaining of this talk, of course, I'm going to tell you what is the maximum possible jump size, because we want to see if this is observable or not. So I'm going to, you know, fine tune the phase to be, you know, around here. And as we do, well, you know, you might say, okay, well, this is maybe sounds like a long, complicated calculation. We have implemented several different checks. So the nice thing is that the calculation that we do here, right, which is somewhat of a semi-analytic calculation, it agrees remarkably well with a very slow numerical evolution. So what we've done in these figures, what you see is a numerical klutz model, which is some approximation for how to evolve such an EMERY. And we added in the tidal field for all the time, right? And as you can see, what happens essentially is that for most of the time, the angular momentum and the Carter constant are not affected at all by this tidal field. And only here is the evolution affected by the tidal field. And that, you know, that jump, right, that one agrees with the semi-analytic calculations that we did here. So this is a very slow and costly evolution. And what we've done is we've shown that, you know, we can get essentially this jump result very effortlessly, you know, much easier, much faster using the semi-analytic calculations, and it matches extremely well. So now you may say, okay, well, that's cool what you told me. Okay, we see that we get some jump sizes. Now we need to see what is the effect on the waveform. So there are multiple ways you can go about this. You can first, or what you should ultimately do, is make a complete waveform model. That is complicated. So what you first do, before you go and do that and invest lots of efforts, you first going to say, okay, I want to know a rough estimate how much it will affect my waveform model without actually making such a waveform model. And that way the way to do that is to say, okay, we're going to focus on this omega phi. And because as it turns out, omega phi is the thing that you measure in a way most sensitively with your gravitational wave detectors. And we're going to look at two different models, one where I take the resonance into account and one where I do not take it into account. And so that means that's the reason for the delta phi, omega phi, one with resonance, one without. And then I'm integrating this, and integrating this will give me the phase. And from the time of the resonance until, you know, the black hole merges into the central massive one. Well, a little bit before it plunges, but minor detail. And if this phase is bigger than, say, 0.1 radian, roughly, depends a little bit on the strength of the signal and all these other details, but roughly, you know, the number you should keep in mind, if it's bigger than 0.1 radian, then it is observable. So let's see what happens. Well, you know, for that random case that we picked, right, this type of resonance around a slowly spinning black hole, we see that the log of this phase thing is, well, you know, shown here. In other words, we should check, you know, where is it larger than 0.1? Well, since I'm showing the log here, it's larger than 0.1 whenever it's larger than this bluish line here. In other words, it's pretty much larger, or it's pretty much observable everywhere within this parameter space. For where here I've shown you the eccentricity, and here I show you the orbital inclination, or actually the cosine of the orbital inclination whenever the resonance happens. And this is, of course, you know, I'm assuming a bunch of numbers here, right? Because otherwise I cannot show you numbers. So here I'm assuming, again, that the massive black hole is that of the mass of Sagittarius A star, and the two small black holes are both 30 solar masses, and it's at a distance of 5 AU, that canonical distance from before. But as we can see, this is pretty much observable anywhere, and it's, you know, actually, in fact, in some parts of the parameter space, right, it leads to a lot of dephasing. And this, you know, is true for slowly spinning black holes. It's true for fast spinning black holes. The shape is slightly different, right? As you can see, it's still, you know, observable in pretty much most of the parameter space. And of course, right, I'm showing you this for specific numbers, but if you want it for different masses and distances, all you need to do is rescale these things in this particular way, and you get it for different values. So the upshot is, okay, we should really model these things. We should really make a waveform model, because if we indeed have tidal perturbers nearby, they are important, right? We should make a waveform model, because this is much larger than 0.1 radian. And that's still ongoing work.
Just to clarify, when you say waveform model, you mean for gravity waves?
Yeah, for the data analysis people
presumably you said only in LISA, right?
Yes, and this again will only be interesting for LISA, because LISA is the only observatory that we have available in the millihertz regime, which is where these systems emit gravitational waves. Yeah, that's correct. So this is, you know, ongoing work. Here I'm just showing you that essentially the uptake is, this is a mismatch. You want that number to be as small as possible. And here we showed for 4 different types of resonances that, you know, if you have some model and account for it, your mismatch is small. But if you don't properly account for it, your mismatch is large. So that you don't want. But this is ongoing work with 2 PhD students and Alvin Chua. So to summarize these tidal resonances, right? If we have, you know, we're going to see LISA and we get data, and there is, so to say, a tidal resonance hidden in there. If we do not correctly identify it, right? If we don't have a model for it, we might say, hey, this is interesting, you know, our model, you know, our just pure GR isolated system model, it's not correct. And voila, we have detected deviations from general relativity, and now, you know, everyone's happy and is going to talk about their favorite model of modified gravity. But in fact, right, what we should really, so that would in fact be incorrect, right? So we should have models that allow us to detect these type of resonances. And when we actually do that, I think it's quite exciting because it gives us very valuable information about the environment near massive black holes. And so these very massive black holes, we cannot really see very well. They're typically far away, except for Sagittarius A star, but we don't really see the neighborhood very well. Even for Sagittarius A star, we don't really see things that close to Sagittarius A star. You know, even the closest S star is about, I think, 200 AU, so much farther than that 5 AU I'm talking about. So we cannot really see close to these massive black holes. We can see, you know, these light black holes, these EMERYs, because they emit gravitational waves, but those tidal perturbers, they're too far out to, you know, emit strong enough gravitational waves. So those we don't see. So there's really no way, at least, you know, not through electromagnetic observations and not through gravitational waves directly of those systems to see them. But, right, they do have an imprint on the EMERY. So if we properly detect them, we can actually learn about these next closest black holes, or, you know, stars or something. It doesn't really matter for our model what exactly these objects are. Through these types of tidal resonances, which I think is quite exciting. Of course, you know, it adds all kinds of extra complications to your data analysis models, etc. But I think it's quite a nice new way of learning about these environments near massive black holes. Any questions about part one? And let me see, I'm chatting way too much. I can skip part two and leave it here, or I can, well, up to you.
Wait, let me see. So it's, maybe could you perhaps just summarize it in a couple of slides, or just, you know, we've gone through this. I
can do it quite quickly.
We'll just wait for the questions at the end so that, yeah.
That's good. I'll do that. Yes. So the second idea is, okay, now let's, you know, forget about black holes and focus on neutron stars. Neutron stars, quite complicated, lots of matter. So let's just focus on two of them, because black holes, you know, are such nice vacuum solutions. You can do quite a bit analytically, but, you know, with all this matter flowing around, things are more complicated. And here we have the same kind of principle, right? So the idea is we can learn about the properties of the system through something actually that people call neutron star seismology. So seismology in the sense that you sort of look at the earthquakes, if you want, of neutron stars. So the principle is easy. If I can excite one of the natural modes of a neutron star through the tidal interaction between the two, right, in this binary. And whenever that happens, the binary will lose orbital energy to this mode, and that can lead to a phase shift, which we might see with gravitational waves or not. Now, this kind of phase shift you can estimate. It depends, of course, on the frequency of the natural mode of the neutron star. It depends on the strength of the mode, so to say, or the interaction between the mode and the neutron star, and the mass and its radius. Now, neutron stars have a bunch of different types of natural frequencies. So we have the fundamental frequency. That is one, for instance, that we will not see with LIGO because its frequency value is way too high. It's outside of the LIGO band, right? LIGO will see maybe up to, well, a few hundred, but not up to kilohertz. Then there's some other frequencies. So you have, and they all get different names, right? The neutron stars systems, they get like the P modes, which stands for pressure modes. the G modes for gravity modes. So not gravitational waves, but these are the gravity modes of the star. They have to do with the sort of the restoring forces, the buoyancy force. You have these R modes, which have to do with the rotation of the star. Anyhow, upshot is all of these modes we likely do not see except for possibly the R modes. But there's one mode that's very interesting to us in this story. And that mode is called the interface mode. So interface in the sense that this is a mode that lives at the intersection of the core of a neutron star and its crust. So you can roughly model, to zeroth order. You say a neutron star is a very dense star. There's some fluid, which is the core, and then the crust, which is the outer layer. And this mode is interesting because it has a frequency, depending on, of course, on the details of the neutron star, that is between 30 and 200 hertz. It has a Q factor that's relatively large, in the sense that this can lead to quite, based on this sort of, astrophysicsy formula, can lead to a dephasing that seems quite significant. But again, if the number to keep in mind is like 0.1 radian. But in fact, actually, the story is even more interesting than just this large dephasing. And that's what I want to tell you. So let me skip this slide. The story is more interesting because it's not going to lead to that much dephasing, but it's going to cause the neutron stars to melt, the crust to melt. So what do we see in this plot? We're going to go over it very slowly. So we're starting, as time goes on, right? Initially, the two neutron stars are far away, and as they emit gravitational waves, they're getting closer. So time, in a way, goes from right to left. And what we see is for this type of neutron star, I've picked, or binary system, I picked, two standard neutron stars of 1.3 solar masses with some particular type of equation of state that tells me what kind of matter it's comprised of. For that kind of system, the I mode frequency is 190 hertz, as you see up here. Now this mode, right, typically it gets excited if the orbital frequency is close to the 190 hertz. And as you know, the gravitational wave frequency, or if you don't know, gravitational wave frequency, if you multiply it by 2, you get the value of the orbital frequency. So as you can see here, this is the gravitational wave frequency. So about here, this starts to match the orbital the orbital frequency, and right, the I mode frequency start to match. And as you can see, that means that if I now look on the left, that the amplitude of the I mode, right, slowly starts to increase, right? Its value becomes larger as I excite the mode. So the mode is being excited. And that's interesting. So as the mode is excited, what happens is, right, the energy in the crust is getting excited. And in fact, what you see is that slowly near the equator, in fact, the crust starts to melt. Right? So initially, right, you have, if the deformations are right, the force is very small, you just get elastic deformation. So things, move, but they get back. But once the force, the tidal force is so strong, right, once the mode is getting large, you get plastic deformation. So these, which means, right, that things are permanently displaced. And when these things are permanently displaced, this causes heat, right? And that heat gets transferred and, makes this crust, this solid crust, makes it melt. And that's what you see. And as as the mode gets more and more excited, more and more of the neutron star gets melted until, in fact, actually most of the neutron star is melted. And at that point, right, when now most of the neutron star is melted, you see something interesting too. That frequency, right, the I mode frequency, right, it was a mode that lived on the boundary of the crust and the core, but now we don't really have a crust anymore because it's all of it is melted. So that mode no longer exists and its frequency just drops to 0. And this kind of cool thing, right, it happens pretty quickly, right? As you see, this distance between the two becomes smaller, and this happens, within, say, 20 orbits as the two go around each other. So quite rapidly. And again, this is a phase shift, something that you can see depending a bit on, well, what the exact value is of your I mode, of that interface mode. And the exact value of that depends, of course, on what your core and your crust are made up of. So this is a kind of interesting. So this tells you right here, you see different equations of state, and they have different frequencies. And so if we were to see such a system, right, if we were to see such a resonance, then we could also learn again about the equation of state through seeing this kind of melting. And well, I did not do such analysis, but we had a student that was very good with the data analysis, and he looked at some of the recent events where the conclusion was that, well, we can't really tell if such a resonance occurred or not, because our data is not clean enough yet. But if we, for instance, look at the advanced LIGO, and certainly with under some optimistic assumptions, and certainly with the Einstein telescope and Cosmic Explorer and other third generation experiments, we should be able to tell if such a resonance occurred. So this is, kind of a fun, different type of resonance that could help us understand what's going on in the insides of neutron stars. So, as I said, right, the tidal interaction, let me quickly summarize. In a neutron star can excite that core-crust interface mode, the I mode, and this can melt the crust and change the waveform. And for now, the analysis, is in a bit, again, crude and in the sense that we use Newtonian perturbations on a relativistic background. But of course, we want to make our model better, and work is in progress to make it a fully relativistic calculation where, also the perturbations are treated properly relativistic, not just the neutron star background. Thank you. I hope this says thank you. I Googled it.
Thanks, unfortunately, I don't know how to read Kannada either. To multiple languages, right? So I don't know how to read it, but I'm sure someone.
Oh, yours, okay, good. Well, then, at least no one will be offended if it doesn't say thank you, or you will not be.
All right, so thanks a lot for a very interesting talk, Beatrice. We have time for some questions, so please, I'll leave the floor open to, because I've already asked a bunch, but I, of course, will if there are no other questions of people. Question by Srihari. Please go ahead, Srihari. Anyone else have a? Okay, so he says, does the L2 also change in the resonance?
You the angular momentum squared.
Yes.
Yes, it does. Yes, yes. The angular momentum squared also changes. Yeah. So I didn't show that plot because typically to describe the orbital evolution, the sort of the relevant constants of motion are only the z component of the angular momentum, and then the Carter constant and the energy, and not the angular momentum squared. But if you were to look at the angular momentum squared, you also see that it changes. Yeah.
So he's asking, so the loss of angular momentum is into gravity waves?
That's correct. Yes. Yes. It all goes into the gravitational waves.
Does that mean, for example, that it slows it down, or that would what is how one would imagine?
Yeah, in a way you can, well, you can think of the orbit indeed, well, either being slowed down as it goes through resonance and evolves inward, or in fact actually goes faster than you would have expected if the resonance didn't occur. So that actually depends on sort of the sign of the sign of the change in orbital in these things, right? So you can have both ways, right? So you can either, I don't know, go faster or slower depending on the sign of this.
So in the case of the resonance that you had in the two, sorry, I'm just going to jump in because I can't see any other questions, but in the case of just the two, the EMERY one, where is the transference of that? I mean, I think you were starting to tell us, but with, there isn't a third. So is the similar kind of thing that happens in so I couldn't tell whether there was a qualitative difference in the 3-body case versus a 2-body case in terms of what the resonance does. So there is a transfer energy, but then what is the physical changes to that process that take place? That's sort of the question.
Yeah, good. So actually in both situations, if I just look at what the EMERY does, it does change the orbital evolution of the EMERY, and that's it. So mathematically, in a way, it's very similar. Now, the two really distinguish themselves in the sense that, what is the cause of the change, right? So in one case, it only has to do, sort of the resonance is caused by the system itself, by the gravitational waves. And in the other case, it's a transfer of the tidal force that is changing the gravitational waves. So it's really, what's the cause? And luckily, from a data analysis perspective, you could tell what the difference is because of sort of the resonance structure being richer in one context than in the other and things like that.
Okay, thanks.
Yeah, that's a good question. Yeah, so luckily, mathematically, things are
okay.
somewhat, analogous.
Do we have any more questions? Does anyone want to ask? Again, I really wish you were here in person because I'm sure there would have been a lot more interaction. So
that's okay. Yeah. That's how
online talks go. Yes.
Exactly.
Yeah. So Srihari has another question, so he's going to ask you another question. So I think he and I will keep you busy for a few minutes. Go ahead. Yes, please, Srihari.
Yeah, I welcome any question.
Yeah, Srihari, you can go ahead and ask. Oh, you can't unmute, but you can you write your question? Okay, thanks. Yeah. So we're going to wait. So the other question I have.
Can you hear me now?
Yeah. Oh, we can hear you now. Yes.
Yeah, sorry about that. So there was some problem with my audio setting.
Yeah.
Can I just ask by voice then?
Yes, of course, please. Yeah.
Okay, all right. Yeah. So this is a basic question. So I just was wondering about the test particle. So when you relax that, so a test particle, is that zero size particle or a zero mass particle? So I was just not sure about
zero size. Yeah.
Okay.
And then in this sense, the key property of a test particle is that it doesn't affect the space-time, right? So typically we know from general relativity, right, that any mass will curve the space-time and change it. But the way test particles are treated is typically we give them a mass nonetheless, but we say, okay, well, but they're not changing the space-time structure. They're only sort of probing it.
Your a small parameter seem to be a mass, so mu over something, right?
Correct.
So
Yes.
is the thing that as you increase the size of the particle, you also increase the mass? So is that why you characterize that by a mass, or so? Why it should have been a size? No, I mean, if you're relaxing the test particle assumption.
Yeah. So for a black hole, the mass and the size are coupled anyhow, right? Through the.
Okay. All right. So that's
yes.
why you think
Yeah.
of it as a mass. Okay.
Yeah.
All right.
Because,
yeah.
Yeah, because the mass also in yeah, we think of the mass as being non-zero even for a test particle, but yeah.
So a test particle with zero size and some mass can also be considered, and that would be a test particle, which would be
Yeah.
following, so that would be fine, right?
Yeah, correct.
Okay.
Yeah.
All right. Thank you.
It's very much similar to like I guess some calculations in I don't know, where we look at the Lorentz force or something, right? If what does an electron do in a electric field? Well, of course, the electron also changes some background electric field in principle, but well, depending on which scenario we were looking at, right? But we're ignoring that back reaction often.
Okay, thank you.
Yes, actually related to this question is, although you had a black hole system, somewhere along the line, I'm not sure, if you just replace it with some axisymmetric system, where is a black hole? Precisely what you were saying about the fact that the size and the mass are related, but where does that come in? Can you tell a black hole system resonance versus just the other three-body system resonance? And are there resonances in other three-body systems? It's kind of a question.
Yeah, excellent questions. Okay, I am confident there will be other types of resonances in non-black hole systems. So for the purposes of this talk, or for this type of resonance, actually, to be honest, it doesn't really matter what this object is, whether it's a black hole or a neutron star or some other system. It just needs to have a significant or a mass of a few solar masses, but that's all we cared about. So in principle, you can put anything there. For the central object, it really needs to be a black hole, as described by general relativity, a rotating black hole as described by relativity, because we need all the symmetries of the background to describe this whole system, right? My entire calculation would break down. I'm using geodesics. So for this one, it's key. Now for this one, as it turns out, you could, okay, so it's easier for the story for it to make a black hole because it's simple, but you could say, okay, well, maybe it's not exactly a black hole, and sort of treat the corrections from black holeness, so to say, as small deviations. But luckily you can do that sort of simultaneously, and you don't need to do that, right? You can sort of say, okay, this is a different small parameter, so you can account for that in a way completely separately. And people have sort of studied that a bit. As it turns out, it mostly doesn't, unless of course this is a crazy wild object, but for most systems, it doesn't really matter what this object is very much. The story is not being changed significantly.
Okay, thanks. Is there, Srihari, do you have another question? Or maybe, yeah, okay, I guess the hand's up. So maybe we can, I'll just see if there's any other questions at all. But I will actually end perhaps with one last question. Yeah, okay, so Srihari doesn't have any more. So I'll ask you one last question, which is about the melting of the neutron star. So you have this resonance, and in slowly, melts, and the whole thing is melted, at which point this mode disappears.
Yes.
And then once it disappears, it just seems to me that the crust would reform, right? Or would unmelt again. And then you'd, is that the case? Or what happens post this, just physically, what kind of, are these sort of periodic things that you would expect then to happen? Whereas it's...
Yeah, no, this is a really fun question. So I guess if this were to happen, So this type of resonance happens already quite close when the two objects are quite close. So
Okay.
the system doesn't have so much time anymore to, you know, restructure itself and become a solid.
Yeah,
So
okay.
in this situation, it makes the question irrelevant because the two merge.
Right.
But
Okay.
indeed, if that frequency were different, you know, a bit further out and then things like that, you might indeed get something periodic or something. Yeah.
Yeah, or at
But
least
just-
semi-periodic kind of.
Yeah.
At least, right. So
Yeah.
that's really interesting.
But-
So I guess, yeah. So this is in addition to the neutron star binary collapse, you would have this surge of a gravity wave that would come that would be characteristic. And so this is also very interesting that you say that, because, you know, we've heard lots of talks about alternatives to GR and trying to attribute, you know, things that are deviations from the standard one. So this could add significantly. So thanks a lot, Beatrice. I, for one, really enjoyed it. And I think we will have discussions on our floor, at least, about your talk. So I'd
yeah, enjoy.
Yeah. So thanks a lot again. And let's give a hand to Beatrice again. And
thank you very much. Yeah, it is.
It was a pleasure to be with you.
yeah, so thanks a lot.